Beautiful. Well, good morning, EuroRust. How are we feeling on the second day? We're going to kick off with some C to Rust migration talk. We will be covering both the strategic aspect, so how you would go about doing such a migration, about planning such a migration, as well as the tactical aspect, the little challenges you'll find when you're working on modules that not necessarily can be cleanly ported to Rust idioms. Before we get into the content, let me get introduced. My name is Luca Palmieri, and I work as a principal engineering consultant for Maymatter. Maymatter being the organizer of EuroRust, as well as a consulting company which, among other things, specializes in Rust. Myself, I've been in the Rust community for 8 years. I've been writing a bunch of open source libraries, open source tools, but I'm probably best known as being the author of Zero to Production in Rust, a book that teaches people how to do backend development using Rust as the underlying technology stack. I'm also the author of Pavex, an experimental web framework, which might be interesting to you. If either of the two things tickles your fantasy, there's links on the slides. But without further ado, let's get into the meat of the talk. Everything we will be talking today happens in the context of a collaboration between Redis Labs, the company, and Maymatter. In particular, we'll be talking about Redis Query Engine. Now, most of you, if I say Redis, think about the key value in-memory store that you may have used for caching or queuing. What fewer people do know is that Redis, over the years, has started to layer additional functionality on top of the key value storage. In particular, Redis Query Engine allows you to define indexes that let you search in a structured manner the key value data that's stored inside your Redis instances. For example, you may try to find all the item identifiers whose description contains either the words Bluetooth or headphones and whose price is in the 070 bracket. The kind of query you might do in a SQL or NoSQL store of your choice. Pretty neat stuff. As a project, Redis Query Engine is a C code base. It counts 63,000 lines of production C code, discounting tests, benchmarks, and other auxiliary artifacts. Redis, as an organization, has decided that they want to migrate this code base from C to Rust. What that means and what that implies is that they want to get rid at compile time of memory safety bugs. They want to ship a product that is stable, that doesn't crash at runtime because a pointer is null or dangling or because you're accessing something out of bounds, thus improving the experience for people actually using Redis Query Engine. Now, Redis is not new to these kind of things. They've done it before. In 2020, they migrated another extension module named Redis JSON. Redis JSON adds support for JSON as a native data type to Redis, and it was written in C, just like Redis Query Engine. In that occasion, they decided to do a from-scratch rewrite. So they created a new repository on GitHub, aptly named Redis JSON 2, and rewrote from scratch the entire code base in Rust, up until the point they got feature parity with the existing C implementation. Now, Redis JSON is not a big code base. At the point of the swap, that was 1,000 lines of code, a little bit more in Rust, which is very different from Redis Query Engine, which is 63,000 lines. Rewriting this from scratch would be much more complicated. To further complicate the matter, Redis Query Engine is actively being worked on. There's multiple teams of engineers that day in, day out are pushing features, fixing bugs, improving performance. If you were to try a rewrite from scratch, you'd be chasing a large moving target with a very high likelihood of actually not shipping anything at the end of the project. So we decided for a different approach. Rather than trying a rewrite from scratch, we decided to rewrite in place, incrementally. What does that mean? You take your C code base and you look at it as a module graph. Every little square in this fictional module graph is a C header file with a corresponding C implementation. Every arrow signals a dependency, so a module importing another module. You look at it as a graph and you try to find leaves. You try to find nodes that have no dependencies. In this example, at the very bottom, you can see AC and AD. They are depended on by other modules, but they have no dependencies themselves. So you take one of those and you rewrite it as a Rust module. You do a pure Rust module which implements the functionality that that unit is meant to provide, and then you wrap it in a Rust FFI layer. The Rust FFI layer uses C-compatible types and C-compatible functions in such a way that the rest of the C code base can consume the Rust module as if it were a C module. This allows you to plug it in and go about business as usual. You do this again with AD, and now all of a sudden, AA only has Rust dependencies. So rather than going through the C interface, we can also rewrite AA in Rust and now call directly into the pure Rust module for both AC and AD. And you can imagine that you do this over and over and over again, and eventually this whole graph becomes orange. Success, you have rewritten your code base to Rust. Unfortunately, real-world code bases do not quite have such a neatly organized module graph. It's a bit more complicated. This is a snapshot of Redis query engine at the point in time when we started the project. So you can still see, there's some leaves in there. But if you get to the center of the project, the situation becomes a lot more entangled. There's a lot more cycles, and just in general, you need to work a little bit to find a good spot to plug in some Rust code. So your day-to-day reality is much closer to this diagram. So you will rewrite a module in Rust, but you will still be depending on some functionality that exists in another C module that you can't just port yet. And so as you progress over the project, you'll try to prune these calls into the C code base, increasing the island of Rust safety. So increasing the island of Rust code, calling into Rust code under the watchful eye of the borrow checker, which is what we want if ultimately we do want to remove memory safety bugs. Now, if you look at the C to Rust rewrite project from an architectural perspective, as we just did, it's boxes and arrows, right? So you put a bit of orange there, then you do this other module. It's very easy. The reality is a bit messier. So to give you a sense of what it actually looks like to do a C to Rust port incrementally, we're going to zoom in on one of the modules that we ported very early in the project, a TrieMap. A TrieMap, as the name implies, it's a map. So it's a way to associate keys to values. In this fictional example, the keys are strings, cool, biker, bis, and bike, and the values are emojis. A TrieMap, you can think of it as a hash map whose keys are sequences of bytes, and whose value is a generic data type. Could be a number, could be a string, could be a pointer. In this project, in most instances, it's going to be a pointer. You would go about using a TrieMap whenever you're looking for one or two properties. You either want very fast prefix searches. So find me all the keys in the dataset that start with car, card, cargo, etc. Or when you know that the keys that you're going to store share prefixes with each other. The TrieMap is very good at storing keys that share prefixes in a compressed format that reduces the memory footprint at runtime, which is why TrieMap are very often used for example, HTTP routing, because all the routes usually have a tree-style data structure. Now, let's try to build one TrieMap instance by hand, just so that we are all on the same page of what a TrieMap looks like. We're going to use exactly the key value pairs that I showed you before in the slide, so cool, biker, bis, and bike. And as you can see in this specific slide, little spoiler, it is a tree-based data structure. So there's going to be nodes and edges, and the properties I just mentioned will be encoded in the way that tree is structured. We start with a single key value pair, bike and the bike emoji. Pretty easy. We do one node. That node is going to have a label, which is going to contain the key. So the label is going to be bike, and the payload is going to be the bike emoji. Things get more interesting when we add biker. So biker shares a prefix with bike, like bike itself is a prefix of biker. So rather than storing biker inside the map, we are going to store the difference. So we're going to add a child node that stores R as its label and the biker emoji as its payload. So the biker key doesn't exist as is inside the tree. You recover it as the concatenation of all the labels of all the nodes from the root to the node that contains the payload. Then we're going to try to store bis. Neither bike nor biker are prefixes of bis, but we can restructure the tree a bit. So we can split the bike node into a BI root and a KE child. BI is not a key in the dataset, so the node for BI is not going to have a payload. It's just there structurally to ensure we can share prefixes. But structuring the tree in this format allows us to insert bis in the same way we inserted biker. So we just store the difference. We just store an S as a direct child of the BI root. Last but not least, we're going to add cool. Cool doesn't share any prefix with any of the keys currently in the map. So same trick as before, but this time we do it with an empty root. So we make BI a child of an empty root, and then we add cool as another child. That's how you build a TrieMap. And you can kind of get an intuition as to why it does that prefix compression that I mentioned before, and why it's good for prefix searches. Logically, what does that TrieMap node look like? You need to keep track of three pieces of information. You want to know the label of that node. You want to know the children of that node. And you want to know whether or not that node has a payload. So let's take a second to go through the definition of the C implementation for a TrieMap node. I'll give you a few moments to read through it. Pretty interesting, huh? First time I read it, I didn't understand what it meant. So I had to go and read a bunch of supporting code to actually picture together what this was doing. I was particularly puzzled by the ghost fields. Like, what does it mean that here comes another, first letters of each child, and now come the children pointer? Why aren't those, in the struct definition? Well, if you go around and you read the rest of the code, you can piece together that the TrieMap node in memory looks somewhat like this. This diagram took me a long time to make, so I'm very proud of it. And I want three things. Thank you. It takes a fair amount of LaTeX to do this. So there's three key takeaways you want to take out of this diagram. Number one, a TrieMap node is a single heap allocation. All the fields, all the information that the TrieMap node is trying to track is stored into a single slab of memory. That is wonderful on the read path for cache locality. You don't have to jump around memory chasing pointers, it's all there, just like a little offset away. Second piece of information that is important, not all the fields have an offset or a length that is known at compile time. And I did this with color codes. So the stuff that you see in blue, we know how big it is at compile time. The payload is generic, but you know at compile time what it is. Label length is going to be 2 bytes, is a U16, same for the number of children. But the label, the children first bytes, the children pointers array, those depend on the actual length of the runtime label and the actual number of children of that specific node. Like, this layout only works for label length 5 and number of children 3. If you change those parameters, the allocation size changes. So you need to be able to handle this, which is why we have ghost fields, something we'll go back to later. Third important piece of information, this layout is packed. That is what the pragma pack1 directive was doing in the C definition, which basically means there is no padding whatsoever in between fields, which in turn implies that some of the fields might be misaligned. And you can see this here. Oh, let me use the laser, that's cool. So if you look at the children pointers array, so children pointers are pointers. Pointers are supposed to be 8 aligned. But this children 0 starts offset 20. 20 is not quite a multiple of 8, is it? Which does imply that that field is going to be misaligned. And if you work with misaligned fields, you know that they're a pain to deal with correctly. So 3 things. Single heap allocation, variable length fields with runtime determined offsets, and packed layout. Key question, can we do this in Rust only using Safe Rust? Nobody's brave enough to utter. I'll tell you, I don't think so. If you think you can, but you're not, courageous enough, you come and talk to me after the talk, because that invalidates the next 20 minutes. But we'll assume that I'm correct and you can't do this in Safe Rust, which makes it complicated. And so you go look at the C module. There's 1,000 lines of C. It's not just about the TrieMap. There's a lot of specialized iterators. Find all the words between this and this, find all the prefixes, find all the suffixes. Like, we iterate in so many different ways. So we got a bunch of complexities. Like a TrieMap, I don't know about you, it's not a data structure. I kind of implement every Monday. So I need to get familiar with how it works. Then there's a bunch of iterators, and there's a super complicated layout to try to squeeze out the last thousands of performance. What do? Do we just go, go for the kill, rewrite it in Rust, get all the optimization, everything done on the first try? Well, we thought that was going to be a bad idea. So we decided to do something different. We decided to establish a baseline. A baseline in this context is a functionally equivalent reimplementation. So it's a TrieMap that quacks and behaves exactly how you would expect the C TrieMap to behave, but its internals have been intentionally simplified. So we're not trying to squeeze the last ounce of performance, we're just focused on correctness. So if you look at the way we define the node in the baseline, this is what it looks like. You have the same information as the C implementation. So you have the label, the children, we're tracking the first byte of each child's label, and we're tracking the payload. But we're making no attempt to have the single heap allocation layout. We're using some little optimizations. Our VECs are low memory versions. They use U16s as capacity and lengths. But other than that, this is, gonna chase pointers at runtime. But that's not a problem, because we have 3 objectives that this baseline can satisfy. Objective number 1, we want to deepen our understanding of the original implementation. We want to try to implement something that passes all the tests and has the same behavior of the original C TrieMap. And the key or goal here is that we want to lower the cognitive load should we then do a second implementation, which is focused on performance. We won't have to think about how our TrieMap works, because we will have implemented one, just a week before. This is about removing some of the things that we need to keep in the buffer of our brains. Number 2, we want an exhaustive test suite. The very nice thing about doing a baseline is that the baseline has exactly the same API of the final implementation, whatever that final implementation is going to be. So any test you write against a baseline is going to stay with you. You can change the internals, it doesn't matter. That test is still going to run. You won't have to change it. So we'll still guarantee that the crazy optimizations you're going to do later are not going to introduce correctness bugs. Now, the C implementation had a bunch of tests already, I think 80-something% coverage, but we added a lot more to get as close as possible to 100%, as well as property-based testing, so to give us something a little bit more robust. Same reasoning goes for performance. It's difficult to know if the baseline is fast enough if you have no way to measure performance. Now, Redis Query Engine does have benchmarks, but they are full system benchmarks. So you spin up a database, run a bunch of queries, measure throughput, measure latency, etc., etc. That's great because you're looking at the database from a user perspective, but the feedback loop is very slow. Like that takes more than an hour to run. And if you are tweaking like the single line to skip some branching, that's way too slow. So we decided to write a bunch of micro benchmarks that did 2 things. Well, tested our Rust implementation, obviously, once again using the public API so that we can keep the same benchmarks later should we change the implementation. And secondly, to compare with the C implementation. So we crafted a Rust API to be able to compare both of them in Criterion using FFI. And the results were pretty good. So coverage-wise, we got to 96%, which is basically 100% because the test coverage tool says that unreachable doesn't count as covered. Well, yes. And 2, we realized that we were not fast enough. So in this violin plot, you can see 3 implementations. The very thin one to the left is the C implementation, also the fastest. It's not just the fastest, its variance is very narrow, which means it's consistently the same speed, which is something you like in a data structure. In the middle, around the 40 mark, you can see our Rust implementation. It's twice as slow as the C implementation, and its variance is a lot larger. Something that probably reflects on the fact that we're chasing pointer and we might be trashing the cache a little bit. And then last but not least, there's another Rust implementation that we took off Crates.io. That's a Radix 3 implementation, because we just wanted a sanity check as to how our baseline was going to do. So our baseline was cool. Well, it was faster than what you could get off the shelf, but no way fast enough to be plugged in for production. And this picture is somewhat consistent across the benchmarks. We're always consistently twice as slow as the C implementation. And if that was not enough to say that this wasn't good enough, we're also we use too much memory. That's because you have VECs, and VECs have to track capacity and they have to track length. And all that metadata, when you sum it together across all the nodes, does amount to roughly twice as much memory, which is not good. So we learned how TrieMap work. We have a bunch of tests and web benchmarks. It's time to let the unsafe flow. Let's refresh our memory. This is what the C layout looks like. Single heap implementation, variable length fields, runtime offsets, as well as a packed layout. We're still not going to go for the kill. In particular, we're going to try to make one simplifying assumption. We don't want to do the packed layout. Misaligned fields are painful. And often they make your data structures lower. So yes, it's a bit more compact, but the CPU really likes where you make aligned accesses. So we're going to try to do a Rust implementation that is single heap allocation, but doesn't try to remove the padding. And then we're going to make a bet that that's not going to use too much memory. So it's going to be faster, and the additional memory usage is going to be acceptable. This is going to be our Rust layout. You recognize the same fields of the C implementation that just shuffled. They've been rearranged in such a way to create a single zone of padding, between the fields that are 1 and 2 aligned and the fields that are 8 aligned. The zone of padding that you see there, like the gray stripes. Worst case scenario, 7 bytes of padding. Best case scenario, no padding. So on average, let's say 3 to 4 bytes. Our assumption is that given the size of the labels that you're usually working with, and given the number of children and the number of leaf node, that padding is not going to be significant. What's the challenge? Why can't you do this in Safe Rust? Node data is a Rust lingo, a dynamically sized type, often abbreviated to DST, if you like acronyms. You've been using DSTs every single day if you've been doing Rust. You've been using slices. Slices are DSTs. Trade objects are DSTs as well. The challenge here is that we need to define our custom DST. What we would like to define morally, if Rust had an infinitely more powerful type system, is a type that looks like this. So you have a couple of normal fields, label length and number of children, a U16, a U8, very boring. And then you have a bunch of arrays whose length is runtime determined by the value of the previous field. Rust can do this, probably will never be able to do this, but that is the layout that we want. So rather than doing this explicit definition, we have to go for something a little bit more implicit. So we're going to have a stack type called node, which is going to have a pointer to the heap allocation, as well as a little phantom data to tell the Rust compiler that, hey, we're generic over the data payload. On the heap, we can't really express the layout of the heap allocation, so we're just going to use the fields which have known length and offset compile time. So if you remember the diagram, those are the blue fields, the one at the beginning. Number of children, label length. We know how much a U16 and a U8 are at compile time. All the green fields, they're not going to be in the definition. We should remind you of the nice comments in the C implementation. It's the same trick. Let's not mention the stuff that's variable length. We'll just handle it manually. Things get really funny when you try to allocate a node. Normally, if you tell the compiler, go put something on the heap, the algorithm, in quotes, that it needs to run looks like this. How big is this type? So how much memory do I need and what alignment should that memory satisfy? Then I'm going to allocate that memory, and then I'm going to put the field values at the correct offsets within that heap allocation. That's what box new does for something that is sized. But here, our type is not sized, so we need to do all these things ourselves. Let's start from the definition of alloc. Alloc is what we would use to put some memory on the heap using the global allocator. It expects a layout and gives you back a row pointer. The layout is going to contain the size and the alignment being a multiple of 2, a power of 2. Layout, beyond containing that 2 pieces of information, it also has a bunch of interesting methods to actually compose manually the layout of a type. So you go to layout and you say, give me the layout of a U16. And then you tell layout, let's extend that with the layout of a U8. And so one by one, we're exactly building the layout of the fantasy data type that I showed you before. We're just doing it manually at runtime, even though, luckily enough, most of this is const, which is cool. Once you have your layout, you pass it to alloc. Alloc gives you a row pointer that we cast to a node header row pointer. And then, we handle the case that the allocation failed. So far, so good. But all the memory that we got is garbage. It's uninitialized memory. We can't do anything with it until we have initialized it. And how do you initialize it? Well, with a lot of pointer operations. So you pointer right the header, then you offset to the right point and you write the label. Then you offset to another field, write it, etc., etc. In the easy case, like a new node, this is tedious. In the complicated cases, like a node split or a node merge, this is very tricky. Which means that we do need unsafe, and we need more than a pinch of it. So the final implementation has 128 unsafe blocks, as well as 21 unsafe private methods. That's a fair amount of unsafe. Which leads us somewhat nicely into the last and probably most important section of this talk. How do you manage unsafe code? I want you to remember what I stated at the very beginning. We're doing this C Rust migration because the client doesn't want at runtime to run into memory and safety bugs. So every time they were introducing unsafe, we're potentially poking a little hole into that promise. We need to be very careful, very disciplined in making sure that the unsafe is correct, because if it isn't, we're going to have undefined behavior, and undefined behavior opens the door to memory and safety bugs. So the North Star is that we want to contain the unsafe. So what we want to do is we want to have no unsafe in the public API of the TrieMap. What that implies is that we will only have to audit the TrieMap implementation for correctness. The rest of the code base, as long as the internals are correct, cannot possibly introduce undefined behavior. That's the nice, powerful thing about using Rust instead of C. And in the case of the TrieMap, this is relatively easy. Like a TrieMap has the same API as a hash map. You insert, you retrieve, you find. This is all very nice, dandy, and safe. But you still have a lot of radioactive material inside, so you still need to manage that. How do you do? Well, a mix of tools and patterns. Tool number one that you want to use, this was mentioned yesterday, I think as well by Amos, you want to use Miri. Miri is a sanitizer that's included in the Rust toolchain that you can use to run your tests under. So Miri is going to run your test in an interpreter, I think that's the correct word, and it's going to check your code against a couple of different memory models, stacked borders and tree borders. And if Miri says that your code doesn't exhibit undefined behavior, that does a big, it's a big confidence boost that you haven't done anything particularly shady. Obviously, that only works if you have tests that exercise most of your code base, most of the branches. So that's why test coverage is so important. And we want it to get as close to 100% as possible. But Miri, is good at telling you that something is wrong. It's not necessarily good at telling you why, unless you've read a bunch of papers. So what I do recommend you is to use the bug assertions liberally. So very often when you do safety preconditions, they can be checked at runtime. You don't do it because you want to squeeze the performance, but you can. So you can check if a pointer is null. You can check if a pointer is aligned. You can check if you're trying to write too many elements into a buffer. The only thing you don't want to do is you want to check that in your production builds. So use the bug assertions. They only run in the bug builds, so they will run for your tests. They will give you a very nice failure message. You try to write 5 children first bytes into a buffer that had 3. That's bad. And you'll be able to debug and iterate a lot faster. Tool number 2, Clippity. Everyone knows Clippy, has a bunch of additional lints specifically for unsafe that are not enabled by default, but you probably should. In particular, in this project, we use 2. We have undocumented unsafe blocks and multiple unsafe operations per block. So what we want is we want every unsafe operation to be in its own unsafe block, and we want every unsafe block to have safety documentation. That makes it so that it's impossible to forget to write safety comments for a specific unsafe operation. And this leads us to the strict approach that we're taking to safety documentation. Now, if you've worked with unsafe, you probably know that there are 2 types of unsafe documentation. If you're writing an unsafe function, then your safety documentation must document what preconditions whoever is using that function must satisfy in order to use it safely. If you're invoking an unsafe function, your safety documentation must explain why those preconditions are met. So these 2 pieces of documentation need to talk to each other. And what Jack Wren is arguing in his article, which I recommend everyone to go and check out because it's great, is that you should write your safety documentation in a structured format, ideally a numbered list, so that it's easier to compare them side to side. There's also an RFC to be able to do this with attributes, which would be so much better, but it's still not here. So if you look at something like the standard library, you have copy non-overlapping to copy bytes from a buffer to another buffer. If the 2 buffers don't overlap, you can see the safety section as a list. It is not numbered, but a list is already a good point. So if you go into our usages of copy from non-overlapping, you see the same little items that you find in the Rust documentation. So a reviewer can look at them side to side and make sure that no precondition has been, forgotten. Nonetheless, that's a very long safety comment. It's what, like 8, 9 lines? We have 128 unsafe blocks. If you do the multiplication, there's 1,000 lines of safety comments, which is tedious. So what you want to do is something slightly different. You want to defend in depth. So just because you have unsafe doesn't mean you can't structure it. So what you want to do is you want to define private APIs that make the unsafe easier to use, which is a different way to say that it's going to be hard to misuse for your colleagues 4 years down the line that is touching your code. What does that mean? We build a hierarchy of abstractions. Let's look, for example, at pointer metadata. So we have been discussing this heap allocation, which has all these fields with runtime determined offsets and length, which means you need to keep track of where those fields are supposed to be. So then you can go and write them or copy them, whatever. We have all this information, so the layout and the offsets, in this pointer metadata struct. But before you're able to use this with a pointer, you got to prove that the pointer and the metadata match. That is tedious if you have to do it every single time. So what you do, you define a higher level abstraction called pointer with metadata. That proof that the metadata and the pointer match each other, you only need to do once when you construct an instance of this struct. After that, you have a bunch of invariants. These invariants are documented at the struct level and can then be used whenever you're doing an unsafe operation to automatically satisfy some of the preconditions. So we're able to offer a way to initialize the children first bytes array to our internal APIs, which has less safety preconditions than the ones you find in the standard library. In particular, those safety preconditions are a lot higher level. So we're telling them that they can't write more elements than there is capacity in the buffer. Sounds reasonable. We're telling them that this is non-overlapping, so the two buffers shouldn't overlap. Also reasonable. And third, we're telling them, make sure you're the only one writing to the buffer. So make sure that morally you have a mutable reference to this uninitialized buffer memory. Also reasonable. We're not talking to them about the fact that the offset needs to be within a contiguously allocated slab of memory, or that the memory needs to come from the global allocator. All of that is satisfied by the invariance of the struct this belongs to. So if you're writing, a new split mechanism, you can use the higher level version. It's going to be a lot easier to get it right. Whew, that was all I wanted to say on Unsafe. A few parting thoughts just to recap what we discussed. We started from a C version, was 1,000 lines of code. All those 1,000 lines, the entire TV was unsafe, so you could have memory unsafety in any part of the original implementation. It had some tests, but no micro benchmarks. We converted that into a Rust version, which is a lot more verbose, almost twice as much code. But the unsafe has been confined to 1/10 of the size of the original C implementation. 128 lines to audit against 1,000. We got excellent test coverage and we got micro benchmarks, which leads to a larger point, that a rewrite is never just a rewrite. It's very often a way to refamiliarize yourself with code that may have not been touched for a while. So to refresh the collective memory of the team, of the company, as to what that code looks like, and also reassess some of the assumptions. We found out in this reimplementation that if you use a non-packed layout, well, you're a fair bit faster. So we beat this implementation in speed. And we also found out that the memory overhead wasn't particularly significant. So this was good enough to ship. And we did ship it. So we shipped this in Redis 8.8, which went out in August. So if you're using Redis Query Engine today, you're running some of our Rust code, which, something we're pretty proud of. And that was only possible because we took a very serious approach at trying to make sure that the code that we were plugging into the rest of the code base satisfied the performance and the correctness and the memory requirements that the original C implementation had. But we also took a chance to kind of challenge some of those assumptions. So what we have now is simpler in many ways than what was there before. And that's all I wanted to say. Thank you very much for having me. If you want to check out the code, is in the repository. Thank you.